Hi there, and welcome back to MA211. We're going to be talking today about pure and practical resonance. Pure and practical resonance are phenomena that happen to mass spring systems when we force them with a periodic forcing function. So first I want to talk about undamped motion, and when you have undamped motion, which means the damping constant is 0, then you can have pure resonance happen in this case. But let's not worry about that for the time being. Let's just think a little bit. So suppose I've got some mass spring system. It's got mass m, it has no damping, and it has a spring constant k. Then you have this ODE governing its displacement from equilibrium, and of course you've got some initial conditions that'll come into effect if you want a specific function and not just a general solution. Okay, so if you solve this guy, we can solve this easily enough, right? You'd write down the characteristic equation is mr squared plus k equals 0, and then you could solve for r, and you'd see that r is the square root of negative k over m, so that would be root k over m times I as your solutions, plus or minus, of course. Okay, and so then you'll have a general solution of this guy, just like I wrote. Okay, so the general solution to the unforced equation looks like this. So it doesn't matter what the initial conditions are. The initial conditions will affect A and B, but they won't affect what's going on here. So regardless of the initial conditions, this thing will oscillate with this frequency right here. It'll be root k over m, and that's in radians per second. If you want to convert that to hertz, I'll leave that up to you. It's not very hard. And that's called the natural frequency of the system. Anytime I ask for the natural frequency of a spring mass system or a spring mass damper system, I mean this thing right here. Okay, I'm looking for the frequency that's inside the solution to the unforced equation. Okay, so now let's suppose that we have a periodic forcing function that I'm adding on. So I'm applying some periodic force to my mass spring damper system, and I want to see how the mass is going to respond. I'm going to use my periodic function will be in this form, cosine omega t, and the omega is called the forcing frequency. And we could go ahead and solve this ODE also, right? But remember, to solve this, we'd have to take a look at the general solution is the homogeneous solution, which we have above, plus a particular solution, and we get the particular solution from the method of undetermined coefficients. And to do that, you just take a guess at what the particular solution might look like, right? So to take a guess, you'd say, okay, well, I have this periodic forcing term on the right hand side, so my guess should be that my particular solution is something times cosine omega t plus something times sine omega t. And that's a perfectly fine guess, unless, remember, unless your guess accidentally solves the homogeneous equation. So this works unless this guy accidentally is in this form, right? So unless omega is equal to square root k over m, then this is a perfectly fine guess at the form of a particular solution. And if omega, your forcing frequency, is not the natural frequency, then you do indeed have a solution in this form. Then your general solution really is a times cosine square root k over m t plus b times sine square root k over m t plus, then you'll have something here, I'll call it small a cosine omega t, plus something else sine omega t. So just as long as you don't force that system with a forcing frequency that's equal to the natural frequency of the system, then you'll get a solution that looks like this. I wrote it right here, and everything will be fine. The question is, what happens if you do force this thing at the natural frequency of the system? This is called pure resonance. Whenever you set omega equal to square root k over m, this is called pure resonance, and this is called the pure resonance frequency of the system. If you have an undamped system, then the pure resonance frequency is equal to the natural frequency of the system. Now let's just take a look at what happens when I force things at the natural frequency. Let's go ahead and we'll start Maple up. I've already got a little Maple worksheet for us. Here I've got the general solution to the unforced system, and you can see our natural frequency for this system is 3 root 2 over 2. What happens if I force this system at that frequency? So inside here my forcing function is 3 over 2 square root 2 times t. If I plot my solution, I get this really weird growth in the displacement of my mass. Let's just go ahead and see what happens if I force this at any frequency other than the natural frequency. I get things that look like this. I get these sort of strange displacements from equilibrium, but they sort of stay relatively small, right? So this one has a maximum displacement of like 0.2, and if I force this thing at say like 100t, then I have a really small displacement from equilibrium, and if I put in a forcing frequency of like 5t, then I also get a fairly small displacement from equilibrium. And you'll see that in each of these there are two parts of my solution. You have this part, the cosine 3 root 2 over 2, that's coming from the general solution of the homogeneous problem. And you've got this second part, 1 over 41 cosine 5t, that's coming from the forcing function. And our displacement is staying relatively small. But just as soon as I force this thing at the natural frequency, and plot the solution, now we see an unbounded growth in the displacement of our mass. And we see that our solution changes a lot also. We get, instead of a term involving sine 3 root 2 over 2t and a term involving, you know, something coming from the forcing function, now we have something involving a t times the sine function, and the t is what's giving us this growth in our solution. So if you were to force a undamped system at this natural frequency, you would observe an unbounded growth in the displacement of the object from equilibrium. Now let's take a look at why that is. Well, if omega is equal to square root k over m, then we have to change our guess at the particular solution. Right? In this case, our initial guess would actually satisfy the homogeneous equation. So in this case, we'd have to take a new guess. We'd have to say that a is t times cosine omega t plus bt sine omega t. And it's this that's getting us the growth in our solution. These t times cosines and t times sines, these are making the solutions grow with time, as opposed to if it were just cosine and sine, those stay bounded. These two grow with time. Only if you force the system at the natural frequency will you see this, and again, this is called pure resonance. So let's move on a little bit. Pure resonance is interesting because you can go from having these nice bounded solutions to solutions that grow with time, but really there aren't physical systems that are undamped, so it's not so exciting. I want to see what happens if we add damping to the system. So now I have a damped system, mass M, damping C, or damping C, spring constant K. I'm going to force it at these different frequencies, and we'd like to see what happens. And just like above, if you force it at one frequency, we'll get somewhat different behavior of the solution than if I force it at a different frequency. So let's just do a couple examples of this. So let's see. This is the ODE that I want to solve. I have a mass of 1, damping constant of 4, spring coefficient of 13. I've gone ahead and chose some arbitrary initial conditions. The initial conditions don't really matter. I'm going to say that I'm only interested in the long-term behavior of my ODE. So when I plot my solution, I'll plot it on a long time scale, and then my initial conditions won't matter very much. So if I force this system at a forcing frequency of 1, then this is my solution, and if I plot it, we can see I get a displacement from equilibrium of, maybe 0.07 or something like that. If I force this thing with a forcing frequency of 5, then we can see I really get a smaller displacement from equilibrium. In the long run, this mass will be displaced from equilibrium about 0.04 units. And if I force it with an even higher frequency, say 50, then I get an even smaller displacement from equilibrium. So the question is, what's the forcing frequency that gives me the biggest displacement from equilibrium? And that forcing frequency is going to be called the practical resonance frequency. Again, I'm only interested in the long-term displacement of the system. So let's see. Alright, so let's try to find the resonance frequency for a given mass spring damper system. So first we'll set up the ODE governing the system. So we have M, C, and K. And then we'll put just a general forcing frequency here, and we'll solve everything in terms of omega. So that what we can do is we can pick off the steady state portion of this solution, and that'll tell us if we have forcing frequency omega, then the steady state portion of the solution is this, however it turns out. And then once we have that, then hopefully we can get the amplitude of the steady state part of the solution. So that'll tell us if we have forcing frequency omega, this is the amplitude of the steady state portion of the solution. And then we'll try to choose omega to make that forcing, or to make that amplitude as big as possible. So first, I've done some work over here. Let's solve the ODE. Here I've solved the ODE that we wanted to in terms of omega. We need to pick off the steady state portion of the solution, and that's sitting right here. It's negative omega squared cosine omega t plus 4 omega sine omega t plus 13 cosine omega t. And I want to write that in a very certain way in just a second. So here I've pulled off, this is the general solution to the ODE right here. I've pulled off the steady state portion of the solution, that's right here, and this is the transient part. Notice the negative exponentials. So this is the steady state portion of the solution, and that's what I'm interested in. I got this just by copying and pasting the line above, and here I've factored things. I've used the maple command collect to factor everything, and I said factor out the terms that have sine omega t and cosine omega t in them. And here is what you get. You get that the steady state solution is this thing times cosine omega t plus this thing times sine omega t. So let me copy that down. Yp is negative omega squared plus 13 divided by 169 minus 10 omega squared plus omega to the fourth times cosine omega t plus 4 omega over the same denominator, 169 minus 10 omega squared plus omega to the fourth times sine omega t. So all I've done here is I've solved this differential equation in terms of the forcing frequency omega, and I've written out the steady state portion of the solution. And again, to find the resonance frequency, I'd like to find the omega that makes this thing have the largest possible amplitude. Notice that this is a sum of sines and cosines, so it's going to be oscillating back and forth with frequency omega. I'd like to say, what's the biggest possible amplitude you could get out of these functions? To do that, notice we have things in terms of sines and cosines, but it's not exactly clear what the amplitude of oscillation is. It's clear that the frequency is omega, but it's not clear what the amplitude is. To make it easier, I'm going to write my solution in this form. I'm going to use a trig identity. The trig identity says that any coefficient times cosine omega t plus any other coefficient times sine omega t, just as long as these frequencies in here match, then that's equal to the square root of a squared plus b squared times cosine of omega t plus phi, where we can easily calculate the phi. The phi is called the phase shift. And I'm not going to worry about calculating it. It's easy to do with an arctan. But if we do that, then we can see, look, it's easy to calculate the amplitude. If I rewrite it like this, it's obvious this is the amplitude of oscillation here. So this is good. I can rewrite my steady state solution as one coefficient times cosine of omega t plus phi. So yp is equal to, I'll write a capital A here for the amplitude, of cosine omega t plus phi, where the amplitude is the square root of this thing squared plus this thing squared. Note, it doesn't involve the sines and cosines. People always want to leave these sines and cosines in there. That's not right. So it's the square root of negative omega squared plus 13 over, what's that denominator? 169 minus 10 omega squared plus omega to the 4. That's the first coefficient in front of the cosine. So that coefficient squared plus the other coefficient squared for omega divided by the same denominator, 169 minus 10 omega squared plus omega to the 4, that guy squared. And I took the liberty of simplifying that for us using maple. You can see it's actually equal to, I simplified it, it's 1 over that denominator, the square root of 1 over that denominator. Alright, so what's this tell us? This quantity tells us if we force with frequency omega, the long-term amplitude of oscillation is this. Right, so let's go ahead. I've plotted that over here. I've plotted our expression for the amplitude in terms of omega. And we can see that right around here, right above 2, there is a maximum. So there is a driving frequency that gives us the biggest possible amplitude of oscillation. You could find it graphically, it's just above 2, but we can also find it analytically. Look, we have a function of one variable, omega, and it tells us the amplitude of the response. We would like to maximize that response. Let's see, so here we've plotted A of omega, and we approximate the resonance frequency maybe using this. We could approximate that the resonance frequency is something like maybe 2.1 or 2.2. We can do that, but we could also just say, well, look, I'd like to maximize this one function. I could calculate dA d omega. If I want to find its max, I could set it equal to 0 and solve for omega and see what happens. So if I try that, just a little hint, you probably want to simplify that. I want the derivative of A with respect to omega. I'd like that to be 0, and I'd like to solve that for omega. Oops. When I solve it, I find I get 3 critical points. One here at 0, which we can see is a local min. We have one at root 5, which is just a little bit bigger than 2, and that one's going to be our max. And then we have another one at negative root 5. This graph would be symmetric if I plotted the other half. That's not what I want. So the square root of 5 is going to be our resonance frequency. If I wanted to approximate it, I could do it like that. It's 2.23. So our graphical approximation was pretty good. If we had decided to zoom in, we could have done much better. So our resonance frequency is at omega equals root 5, which is about 2.23. That means that I get the biggest possible amplitude of oscillation by applying a periodic driving force that has frequency square root of 5 radians per second. And that's all there is to finding natural and pure resonance frequencies. This is